And I believe we are live for another Advent of Code 2024, day 18. And what a wild ride it has been. Real quick, while we have a few minutes before day 18 starts, I want to go back to day 17, um, kind of just discuss the problem and some observations I had after the fact in digging into the code a little bit further and why our day 14 solution worked as well as it did. And not that it went well, but once we had a solution, it worked well. And so I put together this, and this is a representation of day 14, or I'm sorry, day 17, as it was laid out for me. And one of the things we did was we wanted to produce a number. And so in this case, the answer was 167430506, which is what you see here at the bottom. And the way we produce that number is by running the program, which had an operator that we would change the memory registers, it would output a value, and then at the very end, it has the 30, which would cause it to skip back to the beginning, and it would basically loop that process until it got down to 0 in the A register. And so the part that tripped a lot of people up was part 2. Part 1 was a little challenging because you had to implement different functions, but part 2, we had to figure out how to create an input as such that we would reproduce our output with the next, or that we would reproduce the program, this value based on the input provided, and we would have to decide what that mem register was. So the way that we did that is we implemented, I want to first kind of talk about why it worked. So one of the things you notice here is that on each pass of day 17, the 3 bits at the end, or really at the beginning of the number in binary, drop off each iteration of the pass. And so that is the hint that we missed previously, or I missed yesterday, that took some time to figure out. So I'm sharing it here because it's important to understand how this worked. And so you can see each pass, we're dealing with just these 3 bits the entire way. And so because we were dealing with just those 3 bits, we could kind of assert that in order to figure out the inverse, right, or figure out a number, if we want to produce this number up here, we can just deal with 3 bits at a time to get to this value. Now, that number is always reducing every time the program runs. So it goes from some high number down all the way to 0. And so we'll see that here. And so this is just a quick review of an observation from day 17 as to why our implementation worked and how we could have found it a little bit faster had we paid attention to some of the clues about 3 bits and reducing by 3 bits at a time. But if you print out those values in binary, you can actually see it very clearly here, how it's removing the last 3 bits every time it processes after that. So if we go to the part 2 solution, the way that we solved it eventually, and the reason why it worked, is because they said the number would be between 1 and 7, we can start at 0 and try all of the values 1 through 7. So in this case, 6. And if passed into our program, does that produce an output of 0? And the reason we go from bottom up is because we are searching each index to produce that value. And so we would then shift that value to the left for the next iteration. And we would, a shift left for binary is just adding some zeros to the beginning. So like the number 6 becomes 48. And so we would do that at each iteration. And we would then take that as our input, see what would produce the ending of 3, and we would keep on that tree, so on and so forth. This allowed us to skip large amounts of numbers. We weren't going to brute force it when we eventually figured out the solution. And this is why this solution works. And so I just wanted to review day 17 real quick. And after I dived into understanding how the bit operator works in the program itself, and then how that relates to finding the solution in part 2. Because eventually this tree does grow, but it only grows at each layer to do about 172 valid checks to get to this very large number here for the actual solution, at least in my case. So I wanted to describe that because if anybody's getting stuck on day 17, I think understanding this relationship here, and we can real quick before we dive into day 18, if we run the logs here, I kind of put some output that kind of helps articulate that here where, in part 1, that number is reducing each execution. And then in part 2, we do the inverse. We find that last number, and then we branch out the trees at each index layer, doing the additional checks to see if we can move on. Essentially, as pedantic helped out, doing a breadth first search, but minimizing the amount of checks we have to do by actually looking at each bit position, eventually ending up with our result. So that was pretty cool, pretty neat. But let's get focused on day 18 of admin of code. 36 seconds. I'll just get set up here. A couple things. Run that watch mode. All right, day 18, RAM run. You and the historian look a lot more pixelated than you remember. You're inside a computer at the North Pole. Just as you're about to check out your surroundings, a program runs up to you. This region of memory isn't safe. The user misunderstands what a push-down automaton is, and their algorithm is pushing whole bytes down on top of us. Run. The algorithm is fast. It's going to cause a byte to fall into your memory space once every nanosecond. Fortunately, you're faster, and by quickly scanning the algorithm, you create a list of which bytes will fall your puzzle input in the order they'll land in your memory space. Your memory space is a two-dimensional grid with coordinates that range from 0 to 70, both horizontal and vertical. However, for the sake of example, suppose you're on a small grid with coordinates that range from 0 to 6, and the following list of incoming byte positions. Each byte position is given as an XY coordinate where X is the distance from the left edge of your memory space and Y is the distance from the top edge of the memory space. You and the historian are currently in the top left corner of the memory space at 0, 0 and need to reach the exit in the bottom right corner at 77 in your memory space. But at 6, 6 in this example, you'll need to simulate the following bytes to plan out where it will be safe to run. For now, simulate just the first few bytes falling into your memory space. As bytes fall into your memory space, they make the coordinate corrupted. Corrupt memory coordinates cannot be entered by you or the historian, so you'll need to plan your route carefully. You also cannot leave the boundaries of the memory space. Your only hope is to reach the exit. In the above example, if you were to draw the memory space after the first 12 bytes have fallen using for the safe and for the corrupted, it would look like this. You can take steps up, down, left, or right after just 12 bytes of corrupted locations in your memory space. The shortest path from the top left corner to the exit would take 22 steps, here marked with 0 is one such path. Simulate the first kilobyte, 1024 bytes falling onto your memory space. After what is the minimum number of steps needed to reach the exit? Okay. each byte is given by xy, where x is the distance from the left edge of your memory space and y is the distance from the top edge of the memory space. We're at 0, 0. We need to reach the bottom right. You'll need to simulate the following bytes to plan out where it will be safe to run. As bytes fall into your memory space, they make that coordinate corrupted. Cannot be entered by you or the historian, so you'll need to plan your route carefully. In the above example, if you were to draw the memory space after the first 12 bytes have fallen, it would look like this. Okay. 0, 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12. Am I just, is this one byte at a time? Is that what this is? Is this? So, okay. I think I understand. I think I understand now. Well, let me go back to the example though, because I think there's still something here I'm missing. Okay. So, I mean, are these, your memory space is a two-dimensional grid with coordinates that range from 0 to 70. The algorithm is fast, fortunately faster. A list of which bytes will fall in the order they'll land in your memory space. Everything is fast, it's going on a count of byte in your memory space once every nanosecond. Unfortunately, and then what's the minimum number of steps? Simulate the first 1024 bytes. So we have a list here. So if I'm not mistaken, does this just mean that we have our list? We're just going to take the first 12 of these, and then we're going to run a search for the path, and then that's it. So the only thing I don't like is that we don't have the grid size like listed. Let me get rid of this for now. We don't have the grid size listed in the input, but that's okay. We can add it if we want to, or do something else. I guess I could just, because I have test input and I want the test input to be good. So I feel like I'm just going to add the grid to the top for the size. So instead of it being 70 by 70, this one is 6 by 6, and then I'll just parse that out. I realize that's personal preference here, but I think that'll work. And then we just mark where all those are, and then for the first 12, and then we're done with the grid, and then we pathfind it. Is that essentially what we're doing? I think that's it. I have a feeling that the second one is going to have something to do with the timing of we can move as soon as it goes, and then that's where it's going to be a little bit more interesting, meaning that if we can get past a corrupt byte as we go, that might be an option, but that means we'll have to roll. I don't know. I'm speculating on what the next step is going to be, but let's just get this started here. So we know that. Let's go back here and let's grab our 22, and we'll put that in our test input. So we're expecting 22 here. So if we don't use this, and instead we'll just make the first line our size. And then we'll say and we'll call it strings.split, and we'll say string sub s, and then we will give it just a /n. And then size will just be a to I, size s. And then we'll say we'll make a grid the size that we want. Then we'll say for R in G, we'll call this I, and this will be G sub I equal to make slice of string the size of size. And we don't need that. All right, that'll just give us our grid that's already set out to be what the size is. And then for our, what do they call this? Just for, it'll help me in my brain. We'll just call it bytes. Nope, not bytes. Call corrupt. How about that? Slice of ints. And we'll say and then R is going to be we'll do the same for C, and corrupt equals to append corrupt R comma C, and then for now we're just gonna say G sub R sub C equal to that. We'll just go ahead and set it. And then which line is airing? Line 40. Should be fine. See what that produces. Okay, so that is not producing anything. Strings.split. Day 18. It's definitely in that file. And our test is reading from that file. Index at a range 5. Command 48. That's here. Interesting. Okay, so that means that my slice isn't appropriately sized. Let's print out the grid here. And instead, let's do this to be let's just pre-fill it. And let's do that to size. And then we'll do something like that. Let's see if that. That's interesting. Interesting. I was expecting it to. So it's printing the lines there. Ah, there's a space in front of it. That's my bad. 49. Okay. So then we also want, that's fine. We'll do that instead, and we'll split this, and this will be size and call this runs, and this will be 1. Prefer length, actually. And then we'll just say this is doing some extra processing here if we take this approach, but so that should be that. But what's different here than what's here? In the above example, if you were to draw the memory space after the first 12 bytes have fallen using for safe and corrupted, it would look like this. Okay, we don't quite have that. Zero to 70, both horizontal and vertical. However, for the sake of example, suppose you're on a small grid that ranges from 0 to 6. The following list of incoming byte positions: 5, 4. Each byte is given an XY coordinate where X is the distance from the left edge of your memory space and Y is the distance from the top edge of your memory space. Okay. Okay. You and the story are currently in the top left corner. Sure, you need to reach the X at the bottom right corner at 77 in your memory space. But in this example 66, you'll need to simulate the following bytes to plan out where it will be safe to run. For now, simulate just the first few bytes falling in your memory space. As the bytes fall into the space, in the above example, you were to draw the memory space after the first 12 bytes have fallen using for the safe, and it would be like this. It's not what I have. So I'm clearly doing something wrong. So 6 and 12. That's my input. And then 5, 4, 4, 2, 3, 0. They'll land in your memory space. So do these move over time? Is that what I'm missing? Let me just to make sure, let me check to make sure I have. Five, 4, 4, 2, etc. So 2, 0. Okay. So while bytes fall into your memory space, they take the coordinate corrupted. Corrupted memory coordinates cannot be entered by you or the historian, so you need to play into rough cost. You cannot leave the boundary of the memory space. Your only hope is to reach the exit. So, okay, I'll just come back to this. It's given as xy coordinate, where x is the distance from the left edge of your memory space, and y is the distance from the top edge of the memory space. It's the distance from the top edge. So that's just your standard 0, 0 would be top. Yeah. 6, 6 would be bottom right. 0, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5, 6. That's 6, 6. Okay, so that's right. Once a rename in a second, fortunately, you're faster, and by quickly scanning the algorithm, you create a list of which bytes will fall. Puzzle input in the order they'll land in your memory space. Memory space is two-dimensional grid with coordinates that range from 0 to 70. Okay, I got that. Got that. So I did this, and it's not quite right. You can take steps up, down, left, or right. After just 12 bytes have corrupted locations, your memory space, the shortest path from the top left corner to the exit would take 22 steps. Here, marked with 0, is such path. So is it, as bytes fall into your memory space, they make that coordinate corrupted. Coordinates can't be entered by you or the historians. You'll need to plan your route carefully. You also cannot leave the boundary of the memory space. Your only hope is to reach the exit. It says that they fall in to the memory space. What I'm interested in here, why does this look so much different? In the order they'll land. You create a list of which bytes will fall your puzzle in the order they'll land in your memory space. From the left edge. Oh, these are inversed. There we go. Okay. So we've got that. That was terrible. So then, and we need just the shortest path. So I mean, we could use Dijkstra's for that, I guess. We're just looking for cost, right? So how large is our input? I have a feeling if we do Dijkstra's now, it'll be better for us later. Do we need it though? I mean, 70 by 70, I could just step through and I could just add it to the queue and then, but we do want the shortest path. So let's just do it. It'll be fine. It'll be fine, they said. Yeah. So then change this up real quick. Cost will just be how long it's went. We'll leave that. So if we come back up here, this is R, C, this is going to be 0, 0, and this should be RD, RC. CD. And we do something like and this can be just dir, and that's good. And then so we put all those on there from that direction, and then we add something here where we pop it and we say if we'll do something like that. So if our cost is lower, we don't go. And then otherwise, we crawl in all the directions. We'll say if then we break and we return length of p dot path, and or we could just return p dot cost, whatever the cost is to get there. And then I think we just pop all these on in each direction. If g dot inbound, if we're not inbound, R plus RD, C plus CD, then we continue. P dot. So if we're not inbound, we continue, and if P dot R dot P dot RD plus, and then we do the same for P dot C plus P dot D equal then we continue because we don't need to do anything there. No point in putting it on the queue. And then we run that. And then cost is p.cost plus 1. We'll say. Yeah. What's the failure here? Oh, I should probably... We actually know that we don't need to go in all the directions here. We just need to go down. Down and right. I need to mark visited because I didn't do that. That's P. And that should be good there. So actual is still 7. P to R equals C. Once I get here, I don't have to worry about the row column relationship at all. This should be returning cost if our row and our column get to 0, 1, 2, 3, 4, 5, 6. So if we have a size of 6 in our test input, we should be getting here at some point. This is implying that it's not getting there. This should be dir sub 0 and dir sub 1. Also true here. Okay. Oh, and then this needs to be yeah. So where we are plus our dir 0, dir 1. There we go. So now if I take my actual input, I'll just copy it again. Take our actual input, and then I'm going to modify this, and I'm going to put 70, and we want to go for 1024, right? So if I go back here, that is 1024, and we know that we're at 70. And so day 18, go. So if we visited R and C before, if our V cost is less than our P cost, we continue, and our P cost is always our P cost plus 1. Our cost starts at 0. Can we get a print? Um, well, it shouldn't be that many checks. The grid's relatively small. Our visited is that. Oh, you know what I can do? Um, I should also. I feel like I'm missing something here. So if I continue, I mean, just based on this input, if I continue on a specific direction, I should eventually get to the end. But I feel like I'm probably rechecking a lot of the same paths over and over again because the cost here is just relatively equal. So it's crawling out from here. It's having to go through all of that. I could prefer the direction. I don't think that's going to help though. It's not unbound. It's that. Continue to the next one. Cost is always going to be +1. Can I do something where just kind of thinking about how this is going to traverse through here. Let me just run it while I think. Slowing down my stream a little bit though. I mean, this should eventually finish. Unless I miss something. Check the cost. The cost is fine. Let me take out this cost thing here, and we're just going to continue. So I think this, without having like a something that I need to check on every like iteration. Yep, he's not used. All right, cool. We're going to part 2. I think the reason why that was slower is because my cost was only increasing by 1 every time, so that didn't change every time. So now we're on part 2. That my mistake. The historians aren't as used to moving around in this pixelated universe as you are. You're afraid they're not going to be fast enough to make it to the exit before the path is completely blocked. To determine how fast everyone needs to go, you need to determine the first byte that will cut off the path to the exit. In the above example, after the byte at 1-1 falls, there is still a path to the exit. However, after adding the very next byte at 6-1, there is no longer a path to the exit. So in this example, the coordinates of the first byte that prevents the exit from being reachable, 6-1 simulate more of the bytes that are about to corrupt your memory space. What are the coordinates of the first byte that will prevent the exit from being reachable from your starting position? Provide the answer as 2 integers separated by a comma with no other characters. Okay. So when it says simulate more of the bytes that are about to corrupt your memory space, what are the coordinates of the first byte that will prevent the exit from being reachable from your starting position? Provide the answer as 2 integers separated by a comma with no other characters. So I think what we have to do, is we step forward until we find something that corrupts. And then if that position is in our path, so we've got a path, we can add to our path as zero, 0, right? Right. Oh, yeah. Gotta do the extra squigglies here. 0, 0, so that's our path. And then each time we append, we can just path, already have this set up, append path, p.path, and then really it's this, comma, this. Might be better to have some variables for these now that we're here, but we'll figure that out. And so that's going to be your actual path. And so now when we know what the actual current successful run is, how do we want to record that? So we're not going to iterate each step forward. That doesn't really make sense. I think what makes sense is out of the path we have right now, we corrupt until we have something in this path. And then if something does corrupt in that path, what we do is we rerun the algorithm, right? So if we do something like this, and we take this instead, yeah, we'll take this out of here, put it here, and then we've got our G, which is our strings, and then we've got our size, which is an int. What else are we missing here? E.cost, that should all be fine. Why is it not fine? So we actually we want to return path here. So this will be slice of ints. And then this will be p dot path. So we're always going to return our path. So we append it here, and then this remains the same. And so now we set our corrupt bits. And so we want our, actually, let me just return mem, because I feel like I could do a lot more with that. Which has path on it. So it's just P, but it's the dereference version of it because I don't want the pointer in case something changes. And then this just becomes, and this is now get path, and we pass in G, and we pass in our size, and that should be it. And then our score should be for part 1 is actually the length of mem.path. I think that still applies. 252 missing return. Oh, I guess we can return back up empty. 253. I'm going to say that is because we're including 0, 0 on it. And we want steps. So steps would be not including the starting position, which is 252. All right. So now, just to clarify, yes. Yes, so I realized I didn't need it after I started implementing it. I was actually anticipating that problem part 2 is getting more difficult than it was, and it wasn't. So here's my strategy. Well, okay, so here's what I'm gonna do. So I actually have the path, right? So I know what my total path is, not just the count of that path. So now that I have that initial path, what I'm gonna do is I'm going to step forward for the remaining lines one at a time. And each one, and I'm going to have to change this slightly, but it's essentially going to be for range of, let's say, corrupts, which would be like size. Something like that. And we'll call this something like that. And then what I'm going to do is 2 things. I'm going to set R equal to B sub 1 because they're inverse. And then sub 0. And then I'm going to check my mem, what I currently have. I'm going to set this in the grid anyway. But I'm actually not going to recalculate anything. I'm going to check my path to see if R and C exist in that path. And if it does, then after it's set, I recalculate it. Otherwise, I just keep moving forward until I have something that blocks the path, right? And that doesn't mean that there's not another path, but if there's not another path, then I know I found the R and C that is the problem, right? So at least that's the theory here, right? Because if I understand the verbiage correctly, which you guys are probably done already, it says that simulate more of the bytes that are about to corrupt your memory space. So going from 1024 forward. Yeah. So so I want to just see. Um, Unfortunately, I don't think Go has a really good way of doing that with slices of slices. So I sort of just have to make my own, which is not too bad. Oh, Tim, I went like 3 hours and 40 minutes. I actually was very fortunate. Pedantic joined me and really helped me out. Actually, I can talk about it later, but I actually went back through based on what Pedantic helped me through the other night, and I just kind of, this is a learning process for myself as well. I haven't done a lot of these puzzles, and so I'm kind of, I mean, I've done them in the past, but it just understanding what actually happened here, understanding the initial program, like kind of looking back. But I can get into that later. I kind of went over earlier, but then also how that relates to this tree that we ended up going through with doing the bit shifting to actually get to the result. Once I understood what the end result was, printing out the binary form of each number and seeing that the input, the initial program just kind of shaves off that last bit each time to produce the number, really made the implementation of part two that much easier to understand. But let me wrap this up, or at least get there. Yeah, pedantic saved me. So um, if exists, and we'll say that then we need to recalc mem. And I think, oh, I don't know why I modified my part one here. I guess technically it's part two. Let me copy this out real quick and create a part two, or override my part two and fix my part one, because I don't need to do this for part one. Get rid of this. Don't need this anymore. Don't need that. And then this just becomes so return. That's what they want, right? It's a comma delimited. So in the example coordinate, the first byte that prevents X from being reachable, R was 6, 1. Similarly, more of the bytes provide the answer as two integers separated by a comma with no other characters. Well, this actually needs to be D, comma, %D, but we are going to reflip these back into their form, which is comma row, and then this is just going to be returned as none, and I will switch this part 2 to a string for the return. So okay. So if it exists, we recalc it. Otherwise, we do that. And then if we get there, we print it. Let's see what it looks like. 0, comma 13. No, I don't want to just print it. Six, comma 1. Okay, so I am printing that correctly. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 0, 13 blocks here. Yeah, it was, Tim. Yeah. So if I get path, we should be starting a whole new heap here, which I realize isn't necessary, but it is what I'm doing. Visited gets reinitialized. That's fine. That's fine. If we get to the size, we return P. And we're appending our list every time. Um, I was recalculating. Oh, I don't want size here. That's not right. I want length. That's why. Okay. There we go. Just to make sure. Okay. So 6148. Hmm. Um. Ah. Hold on. This isn't flipped. I'm correcting it here with this. So this should be this, not the other way around. And we do need to flip it here still, but this does not need to be flipped. Okay. Five and 60. There we go. All right. Well, cool. That's done. That wasn't too bad. The only thing that really tripped me up is I was not paying attention when I was reading the instructions about the X and Y, and I wasn't flipping them early on initially, which caused things to be bad. And then I may have over optimized this, or overbuilt this, I should say, not necessarily optimized, because I didn't really need to do anything with cost. I was thinking that my thought was that maybe there was going to be something where those bits were going to be falling over time. Which they kind of did, but I thought it was going to be more complicated than that. It's fine. It is what it is. This works. And the optimization here was just, as far as making sure part two didn't take forever because I was checking the path over and over again, was simply just iterate through and only rebuild your path if we end up with a corrupt byte on the path that we already have. Just because we have one that showed up on the path doesn't necessarily mean that our path was blocked, but it means that our path could be blocked or there may be another route. Maybe we could have done something where instead of starting from position 0 every time, we figured out where that point was and we split the slice and kept our current path like -1 step and then started from there forward, which would still give us a path potentially, but it doesn't guarantee a path on that T. So maybe this way is just fine. Anyway, that worked. I guess, I mean, if you guys want to go through this again, Tim, if you guys are interested, but Pedantic did help me out quite a bit yesterday, kind of got me unstuck. And so, you know, again, learning opportunity, trying to constantly like learn here. But, you know, once we walked through the solution and I understood what was going on, I said, okay, well, how can I go back and how could I have seen this in the future? And the answer is if I would have just logged and paid attention to the 3-bit statement that was throughout the problem, there's a lot of text there. But then if I would have logged each pass of part 17, I would have seen that that first 3 bits were falling off each iteration on the very right side of that number. And then, you know, you can kind of see the tree effect from there. So, but hey, didn't do too bad tonight. We check out our leaderboard. I know I'm not on it, but if I look at my personal times and where the rank was at, not great. Not great, but not terrible, I guess. And yeah, so we'll go from there. But thanks for hanging out, guys. I'll see you all tomorrow.